Good morning, everyone. My name is Satyendra Rajput. I am going to give the poster presentation on molecular dynamic study of aggregation of the cyanide dye in the presence of the crowders. So the intracellular the intracellular environment is completely packed with the DNA, RNA, ribosomes, and the various molecules. And the inside the living cell, the macromolecular concentrations are around 25 to 45% of the total cell of the volume. There are less proofs in such a crowded environment that how the proteins keep their original structure in vivo than studied alone. Moreover, the dynamics and the structural properties of the proteins are well characterized in the vitro, but the crowding effect is still elusive in vivo. Therefore, the simulation studies have been conducted which contain the atomic information of the macromolecules till some extent, to see how they behave all together. And at the end, there is a simulated picture of the small fraction of the cell. And there are several theories which are try to explain the crowded environment, but the Asakura Osawa theory is one of the theory which first came in 1954, which came 1954 and is based on the and is entirely based on the depletion forces. So in this right picture, there is a spheres with the purple color. They are representing the crowders, and the yellow one is representing the macromolecules, and the dotted circle around the yellow one is representing the van der Waals radii. When these two macromolecules come close to each other, the van der Waals radii starts to overlap. As a result, it increased the free configurational volume available for rest of the crowders, which increase the entropy, and such process become entropically favorable. This process is known as the depletion attraction, and several computational studies have been conducted to see the crowding effect with solvent excluded volume, to find out how the molecular driving force affect the aggregation in crowded environment. And so in the in the in the in, in the biological system, the protein folds into its three-dimensional structure, by which protein becomes biologically functional. However, protein also, however, when the protein misfold of the however, misfolding of the protein leads to the highly ordered structure is known as the amyloid fibril, and the whole process is known as the amyloidogenesis. So therefore, to model the intracellular environment, uh, we have used the pseudo isocyanine dye, which is hydrophobic and ionic in nature, like the composition observed in the protein. Some experimental studies have shown that the uh, the the PIC dye gets self-assembled into a small stacks in the aqua solution. Therefore, the cyanide dye can be a good model to study the protein aggregation in the crowded environment. So in our simulation, we have used the GROMAC software to model the PIC dye, and then we have used the general Ember force field for the dimer, and then we have equilibrated the system for the 1 nanosecond and the production run for the 5 nanosecond. So the first picture contains the dimer and the protein, sorry, dimer and the ethylene glycol, and the ethylene glycol is like acting as the crowders inside the system. So as we can see in the 14 in the potential of mean force curve, that the global minima occur around 0.42 nanometer, uh, which is where when the dimers are at the closest proximity, and then this the free energy of the association get decreases when the dimer get far when the dimer goes far apart from each other. So this is the potential of mean force in the pure water. Till now we have able to generate the PMF of the dimer in the pure water, but in future we are planning to add some more crowders such as the tag inside the solution, and we are expecting to see some interesting result. uh, that's all. So I'm ending with my talk here. So thank you, IIT Delhi, for providing me high performance computing facility and the junior research fellowship for conducting this research. and and I also wanted to say thanks to the organizers of the CompFlu conference. Thank you.